As 3i Atlas swung closer to the Sun, a journey called perihelion passage in astronomer speak, it started behaving strangely. Not, that's interesting strange. More like, wait, that shouldn't be physically possible strange. The scientific papers started piling up. Observation reports flagged inconsistencies, data that didn't fit the models, numbers that refused to make sense. And with each passing month, as 3i Atlas drew nearer, the weirdness intensified. What you're seeing in these initial images looks ordinary enough. There's a fuzzy blob of light surrounded by a glowing haze. If you showed this to a random person on the street and asked them what it was, they'd probably say, a comet, and they'd be following centuries of astronomical tradition. Comets are supposed to look fuzzy. The word comet itself comes from ancient Greek, meaning long-haired star. That fuzziness, scientists call it the coma, is just gas and dust being blown off the icy nucleus as sunlight warms it up. Hit like and subscribe for more sleepy explanation. Nothing unusual about that. Comets have been doing this since the solar system formed 4.5 billion years ago. But here's where things get interesting. That fuzzy appearance, it's hiding something. Think of it like looking at a distant city through morning fog. You see the general glow of lights, maybe some vague shapes, but the architecture, the actual structure of what's there, remains invisible. The fog obscures the truth. For months, astronomers knew something was buried in that coma. The math suggested it. The way the object moved, the way light bounced off it, the weird flickering in its brightness, all of it hinted that beneath that glowing cloud there was structure. Precise structure. The kind that makes you uncomfortable if you think about it too long. They needed a way to peel back the fog. Enter a technique called the Larsen-Sacchinina rotational gradient filter. Before your eyes glaze over at the technical jargon, let me explain what this actually does, because it's brilliantly simple once you grasp the concept. Imagine you take a photograph of something glowing, then you rotate that same photograph by a specific angle, let's say 15 degrees. Now you place the rotated version on top of the original and subtract one from the other. What happens? Everything that's perfectly circular, that symmetrical glow, cancels itself out. It disappears, because a circle rotated is still the same circle. But anything that's not circular, anything with edges, with structure, with specific geometry, that survives the subtraction. It stands out. It's like using a special filter to see through the glare of headlights and spot the actual shape of the car behind them. A researcher named Tony Scamato published a paper online yesterday utilizing this exact technique on the January 14th Hubble images of 3i Atlas. The paper's available now. Other scientists are already poring over it, checking the math, verifying the methodology. That's how science works. Everything gets scrutinized, challenged, tested. But here's the thing. The technique is sound. The math checks out. And the result? When they applied this filter to the new Hubble data, the fuzzy coma vanished. That blinding glow, gone. And what emerged from beneath it made every astronomer who saw it do a double take. Some of them rubbed their eyes. Others pulled up the raw data to make sure there hadn't been a processing error. Because what the filter revealed wasn't chaotic. It wasn't random. It wasn't the turbulent, messy emission pattern you'd expect from a chunk of ice and rock venting gases as it tumbles through space. It was a perfect geometric pattern, 3 distinct features, 3 jet-like structures, and they were arranged. I need you to pay attention to this number, exactly 120 degrees apart. Let me repeat that, exactly 120 degrees apart. Picture a peace symbol, 3 lines radiating from a center point, each separated by equal angles. Or think of a Mercedes-Benz logo. That's the kind of symmetry we're talking about, precise, mathematical. The kind of arrangement that makes your brain immediately recognize it as intentional. When I first saw this image, my immediate thought was, this has to be an artifact. A glitch in the processing. Maybe the filter itself was creating the symmetry somehow, imposing order on chaos because of the mathematics involved. That happens sometimes with image processing. You can accidentally create patterns that aren't really there. So I know what you're thinking. You're thinking the same thing I thought. The same thing every trained scientist thought when they saw this. Cool pattern, but it's probably just a coincidence. Space is big. Weird things happen. Give me more data. Fair enough. Healthy skepticism is the cornerstone of good science. Never accept the first anomaly at face value. Always demand replication. And that's exactly what makes what happened next so disturbing, because Tony Scamato and his team didn't stop with one image. They went back into the archives. Hubble has been photographing this object repeatedly for months, building up a comprehensive observational record. Dozens of high-quality images taken from November through January. Different dates, different orbital positions, different angles as both Earth and the comet moved through space. The team applied the same Larsen-Secunina filter to 24 separate images, 24 different snapshots across nearly 60 days of observations, November 30th, December 4th, December 12th, December 27th, January 7th. Each one captured at a different moment in time, from a different perspective, under different lighting conditions. If this were a processing artifact, it would appear in some images but not others. If it were a temporary phenomenon, a lucky fracture on the surface that just happened to vent in 3 directions at once, it would show up once, maybe twice, then disappear as conditions changed. But that's not what they found. In every single image, the pattern persists. November, 3 jets, 120 degrees apart. December, same configuration. Early January, still there. Mid-January, unchanged. The geometry remains rock-solid consistent across 2 months of observation, through different phases of the comet's activity, through changes in solar heating, through what should be violent, chaotic processes as ices vaporize and gases blast away from the surface. The pattern doesn't budge. Now, if you're not immediately unsettled by this, let me explain why this is so profoundly weird from a physics standpoint. Comets are not stable objects. They're not solid chunks of rock like asteroids. Most of them are more like dirty snowballs, mixtures of ice, dust, and rock loosely bound together by weak gravity. Some are even what we call rubble piles, collections of debris barely holding together. When sunlight hits these objects, it doesn't heat them evenly. The surface facing the sun gets scorched while the shadowed side stays frozen. This creates thermal stress. Ice sublimates, turns directly from solid to gas, and jets of vapor explode outward. These jets are violent, random, and chaotic. They appear and disappear. They shift position as the comet rotates and tumbles. Think about a log in a campfire. As it burns, gases escape from cracks. The cracks grow. New cracks form. The wood splits. The pattern of venting changes constantly as the structure breaks down. That's what we expect from comets near the sun. Chaos, entropy, disorder. What we're seeing with 3i Atlas is the exact opposite. It's maintaining geometric precision over weeks, that 120-degree spacing. It's not drifting. It's not degrading. It's not spawning new jets or losing old ones. It's stable, unnaturally stable. When I showed this data to a colleague who specializes in comet physics, she stared at it in silence for a full minute before saying, "That shouldn't be able to maintain itself. The thermal stress alone should destroy any symmetry within hours, maybe days at most. I don't know what this is." And it gets stranger. Because the 3 jets, let's call them what the paper calls them, the mini-jets, aren't the only structures visible in these processed images. There's a 4th feature. A massive plume extending in completely different direction. Where the 3 mini-jets are short, stubby, reaching out just a modest distance from the nucleus. This 4th jet is enormous. It stretches 10 times farther into space. It points back toward the sun, what astronomers call the anti-tail direction. So we have 3 short, perfectly spaced jets, plus 1 long, powerful jet, a 3+1 configuration, 3 pointing in one general direction, 1 pointing the opposite way. If you're starting to think this sounds less like a natural geological process and more like something else entirely, you're not alone. But let's not get ahead of ourselves. Let's stick with the data. Let's be rigorous. Because there's more to unpack here, and each new layer makes the mystery deeper. This geometric configuration exists in 3-dimensional space, but we're observing it as a 2-dimensional projection on the plane of the sky. Imagine taking a photograph of a sculpture. You only see one angle, one perspective. The sculpture has depth, but the photo flattens it. Same deal here. We're looking at a 3D object squashed into a 2D image. The fact that we see these jets separated by 120 degrees in projection means something very specific about how the object is oriented relative to us. If the jets were randomly scattered across the surface in 3 dimensions, the chance of them appearing precisely evenly spaced in our 2D view would be essentially 0. It would require an extraordinarily unlikely alignment. But it's not just one lucky alignment. We're seeing this 120-degree separation persist as both Earth and the comet move through their orbits, changing the viewing angle slightly with each observation. If the symmetry were a projection effect, an illusion created by our viewing angle, it should break down as that angle changes, but it doesn't. This tells us the symmetry is intrinsic to the object. It's not a trick of perspective. The jets are actually arranged in a geometric pattern on the surface. Based on the consistency across multiple viewing angles, the most likely configuration is that they're positioned around a plane perpendicular to the object's rotation axis, like 3 spokes on a wheel, equally spaced. Now, I want to pause here because we need to talk about what this geometric precision actually implies. This isn't just about aesthetics. This isn't, oh, neat, a pretty pattern in space. The implications cut straight to fundamental questions about how matter organizes itself in the universe. In nature, microscopic symmetry is common. Snowflakes have 6-fold symmetry because water molecules stack in hexagonal crystal lattices. Salt crystals are cubic because of how sodium and chlorine atoms bond. At the atomic level, symmetry emerges from the laws of quantum mechanics and electromagnetic forces. It's beautiful, yes, but it's also explicable. We understand the physics. Macroscopic symmetry, symmetry at large scales, is extraordinarily rare in natural systems. Go outside right now and look around. You won't find 3 trees growing in a perfect triangle. Mountains don't arrange themselves in geometric patterns. Rivers don't fork at equal angles. Geological processes are inherently chaotic. They're driven by random variations in material properties, by turbulent fluid dynamics, by stochastic processes that destroy symmetry as fast as it might form. Even on other worlds, this holds true. We've studied the geysers on Saturn's moon Enceladus. They erupt from fractures in the ice, yes, but those fractures are random, jagged, scattered. We've mapped volcanic vents on Jupiter's moon Io. They're distributed chaotically across the surface. We've examined asteroid craters, planetary formations, every natural structure we can observe, and none display the kind of regular geometric spacing we're seeing here. Dr. Frank Lorkin reviewed this new data and made a statement that cuts right to the heart of the issue. The symmetric 120-degree angular spacing between these 3 mini-jets is astounding. Yeah, it's hard to imagine such symmetry in a natural macroscopic object. Hard to imagine, that's putting it mildly. Let me give you some context from probability theory. If we assume these jets could appear anywhere on the object's surface with equal probability, and we're looking for 3 jets that happen to space themselves exactly 120 degrees apart, what are the odds? The calculation gets complicated because you have to account for the 3-dimensional geometry and the viewing angles. But even a rough estimate puts the probability well below 1 in a million. But wait, we're not just seeing it once. We're seeing it persist across 24 separate observations. The probability compounds. Each observation that confirms the pattern multiplies the unlikelihood. By the time you've confirmed the same geometric arrangement 24 times over 2 months, you're in winning the lottery while being struck by lightning territory. At some point you have to entertain alternative explanations, and this is where the conversation gets uncomfortable for a lot of scientists, because the alternative explanation, the one that fits the data uncomfortably well, is that this isn't random at all, that the symmetry exists because it was designed that way, that we're not looking at geology, we're looking at engineering. But I'm getting ahead of myself again. Let's stay focused on what we can measure, what we can verify, what we can prove, because there's another layer to this mystery that takes us from static geometry to dynamic motion, and that's where things get truly fascinating. These jets aren't stationary decorations painted on the surface. They're part of a moving, rotating system, and when you analyse how they move, how the pattern changes over time, you start to see something that looks less like a tumbling rock and more like a machine with moving parts. This is where the analysis shifts from what is it shaped like to how does it behave, and the behaviour is just as strange as the shape. Remember, this object is spinning. All comets spin, usually chaotically, tumbling through space like a kicked football. The rotation comes from collisions during formation, from asymmetric outgassing, from gravitational interactions. It's random, variable, unstable. But 3i Atlas isn't tumbling chaotically. the team performed what's called a time series analysis. They took all those images spanning weeks and months and assembled them into a sequence, essentially creating a movie of the object's motion. They measured how the jets moved relative to the background stars, they tracked the angles, they timed the periodicity, and they found something shocking. The entire jet system oscillates rhythmically. The pattern wobbles, not randomly, but periodically. The angle shifts by plus or minus 20 degrees in a predictable cycle, and that cycle repeats with metronomic regularity every 7.1 hours. 7.1 hours, that's the rotation period of this object. That's how long it takes to complete one spin. Imagine a lighthouse on a coast. If the lighthouse beam is perfectly perpendicular to its axis of rotation, like a spoke on a wheel, it sweeps a flat horizontal line across the water. But if the beam is tilted, even slightly off axis, it traces a cone. As the lighthouse spins, the beam wobbles up and down from the perspective of someone watching from a boat. That's what we're seeing here. Each of the 3 mini-jets is behaving like a tilted lighthouse beam. As the nucleus rotates with its 7.1-hour period, the jets sweep through space in conical paths. They're locked to the body, spinning with it, but oriented at an angle to the rotation axis. This wobble, this precession, tells us something crucial about the object's orientation. The analysis suggests the rotation axis is pointed almost directly toward the Sun. We're talking about an alignment within 10 to 20 degrees of the Sun object line. Now here's where it gets really interesting for those of you who've been following this story from the beginning. Back in the August 2025, 5 months ago, some researchers analysed the brightness variations of this object, the way it flickered, the pattern of light and dark as different parts of its surface rotated into and out of view. Based purely on that light curve data, they built a mathematical model and predicted the object's rotational configuration. And they predicted exactly this: an axis pointing roughly sunward, a 7-hour rotation period. At the time, it was theoretical, a best-fit model to explain the brightness data. Now, months later, we're seeing direct physical evidence of matter being ejected in patterns that confirm that exact same geometry. The mathematical prediction from August perfectly matches the observational reality of January. That kind of concordance between independent measurements is extraordinarily satisfying in science. It means we're actually understanding something real, not just seeing patterns in noise, but it also raises new questions. Because a 7.1-hour rotation for an object this size generates significant centrifugal force. If 3I Atlas is a typical comet, a loose aggregate of ice and rock held together by weak gravity, that spin rate is pushing the limits of structural integrity. Centrifugal force tries to fling material off the equator. For a rubble pile, too much spin equals catastrophic disintegration. Yet here it is, spinning steadily, maintaining its geometry, not flying apart. Either this object is much stronger than we expect, made of something more rigid than the typical comet, or there's something else going on, some mechanism maintaining the structural integrity against the rotational forces, and then there are the jets themselves. They're not just visual features, they're rockets. Every kilogram of gas and dust ejected at hundreds of meters per second exerts an equal and opposite force back on the nucleus. Newton's third law playing out in real time. If you have 3 jets firing in discrete pulses, arranged symmetrically, and that arrangement is wobbling by 20 degrees as the object spins, you're introducing complex time-varying torques into the system. Torques change rotation. They speed it up, slow it down, tilt the axis. For a natural comet, these torques would cause the rotation state to evolve rapidly. We'd expect to see the spin rate changing week by week. We'd expect the wobble to grow or damp out. We'd expect instability. But we don't see that. We see the same 7.1-hour period, the same wobble amplitude, week after week, month after month. Something is stabilizing the system. Either there's some internal mechanism, friction, damping, mass distribution, that we don't understand, or the system is being actively controlled. I know how that sounds, I know the implications, but stay with me, because we're going to follow the data wherever it leads, even if it makes us uncomfortable. Let's think about this purely from a mechanical engineering perspective. Strip away all assumptions about comets and ice and natural processes. Just look at what we have. A rotating body with a 3+1 thruster configuration. 3 symmetrically placed jets in one plane, one larger jet pointing the opposite direction. If you were designing a spacecraft and you wanted to control its attitude, its orientation in space, how would you do it? Standard spacecraft have what are called reaction control systems, thrusters, small rockets that fire in specific directions to rotate the craft, stabilize it, point it where you need it to go. For full three-dimensional control, the ability to rotate around any axis and translate in any direction, you typically need 6 thrusters. 2 opposing pairs along 3 perpendicular axes. Fire one thruster, the spacecraft rotates. Fire the opposite thruster, it stops rotating. That's the textbook answer. But spacecraft designers are obsessed with efficiency. Mass is precious in space. Every gram of fuel, every kilogram of hardware reduces your payload capacity. So engineers constantly ask, what's the minimum viable configuration? What's the fewest thrusters we can use and still maintain control? And here's where Now, Lorcan's analysis gets provocative. He noted that if an object is already spinning, if it has gyroscopic stability from rotation, you might not need thrusters along the rotation axis. The spin itself provides stability in that direction, like a spinning top or a bullet from a rifled barrel. So maybe you don't need 6 thrusters. Maybe, if the object spins around its major axis, you only need thrusters in the plane perpendicular to that axis. Thrusters that can nudge the orientation, make adjustments, fine-tune the pointing. How many would that take? 3 would give you control around the perpendicular plane, and maybe 1 more in the opposite direction for major course corrections or velocity changes. 3 plus 1, 3 plus 1. Which is exactly what we're observing. The 3 mini-jets could be attitude control thrusters. The 1 massive anti-tail jet could be the main engine, providing thrust, changing velocity. The wobble we see, that 20-degree precession, might not be instability at all. It might be the visual signature of those control thrusters firing in sequence, making minute adjustments to keep the system oriented properly. This is speculative, yes, but it's not wild speculation. It's grounded in aerospace engineering principles. It's the kind of question that gets asked in spacecraft design meetings. How few thrusters can we get away with? And the answer that keeps coming back is 3 plus 1 might be enough. Now, I need to be crystal clear about something. We are not declaring this object artificial. We are not saying it's aliens and calling it a day. Science doesn't work that way. What we're doing is examining all possible explanations and seeing which ones fit the data. Natural explanations get first priority, Occam's razor and all that. The simplest explanation is usually correct. But when natural explanations require increasingly unlikely coincidences, when you have to stack improbability on top of improbability to make them work, you're obligated to consider alternatives. This is the scientific method in action. Hypothesis, observation, testing, revision, and above all following the evidence rather than our preconceptions. So the question becomes, how do we test this? How do we distinguish between a weirdly symmetric comet and something else? We need a prediction. Something specific that would happen if one hypothesis is true but not if the other is true. A decisive observation that settles the matter. And as it turns out, the universe is about to hand us exactly that opportunity. There's a geometric event happening tomorrow, yes, tomorrow, January 22nd, 2026, that will let us see this object from an angle that's nearly impossible to achieve under normal circumstances. An alignment so precise it occurs only once during this entire passage through the inner solar system. The geometry of space is about to give us an unobstructed view. Let me explain what's happening. Right now, as Earth orbits the Sun and 3i Atlas follows its own trajectory, the angle between us is constantly changing. Most of the time, we see the object from the side, so to speak. We get a profile view. Any 3-dimensional structure gets flattened by perspective into a 2-dimensional projection. But tomorrow, according to orbital calculations published last week by researchers Barozzi and Barbieri, something special occurs. The Earth-comet Sun angle collapses to nearly 0, specifically to 0.69 degrees, less than 1 degree, essentially a straight line. For a brief window, we'll be looking at this object almost directly along the Sun-comet line. Instead of seeing the jets from the side, where they might look foreshortened or distorted by perspective, we'll see them face on. If the hypothesis about the rotation axis is correct, if it really is pointed sunward, then during this alignment those 3 mini-jets should trace a nearly perfect circle as they rotate. Not an ellipse, not a distorted wobble, a circle. Imagine looking at a spinning ceiling fan from below versus from the side. From the side, the blades look like they're moving back and forth. From below, you see the true circular motion. Same principle here. If we see that circle tomorrow, it confirms the axis orientation with extraordinary precision. It also lets us measure the true spacing of the jets without having to correct for projection effects. We'll see the geometry naked, unobstructed. It's a test, a clear, unambiguous test of the rotational model. And there's more. This alignment creates what's called an opposition surge. When sunlight illuminates a rough surface and you view it with the sun directly behind you, shadows disappear. Every particle, every grain of dust hides its own shadow. The result is a dramatic spike in brightness, a non-linear increase that can make the object shine 10 times brighter than normal. This means better data, stronger signals. Fainter structures that have been hidden beneath the noise threshold, they'll pop into visibility. Secondary features too dim to see before, tomorrow might reveal them. Observatories worldwide are being notified. Amateur astronomers with backyard telescopes are being mobilized. Everyone who can point an instrument at this object should be doing so in the next 48 hours. This is the golden window. We're looking for that circle, that ring traced by 3 jets rotating around a central axis. If it appears, if the geometry holds, it's one more piece of evidence stacking up, one more data point that demands explanation. And if it doesn't appear, if the symmetry breaks down when viewed from this angle, that's data too. It would force us to revise everything, but given that the pattern has held solid for 2 months through changing perspectives, confidence is high. The geometry has been stable since November. There's no physical reason to expect it to suddenly collapse now. So tomorrow is critical. Mark it. January 22nd, 2026. The day we get our clearest view yet of whatever this thing is. But here's what really keeps me up at night. This symmetric jet structure isn't an isolated anomaly. It's one item on a much longer list. Because 3i Atlas doesn't just have weird geometry, it has weird everything. Over the past months, as observations have accumulated, researchers have catalogued anomaly after anomaly. Each one, taken individually, might be dismissed as unusual but explainable. But when you list them all together, when you see the full picture, the cumulative weight becomes staggering. We're up to 18 distinct anomalies now. 18 separate characteristics that don't match standard comet behavior. Let me list just a few. The extreme non-gravitational acceleration. This object is speeding up and slowing down in ways that can't be explained by normal outgassing models. The forces are too large, too directed. The spectral composition. When you analyze the light coming off this object, you don't see the carbon-based molecules that should be there if it were a typical comet. The chemistry is wrong. The structural strength. 3i Atlas has survived gravitational stresses that should have torn a rubble pile apart. It's holding together under conditions that should fragment it. The rotation stability. That 7.1-hour period maintained through intense thermal stress and asymmetric jetting. And now, this. The perfect 120-degree jet spacing. 18 items. 18 outliers. Each one has maybe a 1 in 100 or 1 in 1,000 chance of occurring naturally. When you multiply those probabilities together, when you ask, what are the odds of all 18 happening in the same object, the number becomes vanishingly small. It's like flipping a coin and getting heads 20 times in a row. Technically possible, but at some point you start wondering if the coin is rigged. We've developed what we call the LOBE classification scale to assess the likelihood of a technological origin for interstellar objects. It's a framework for quantifying how suspicious something looks. How many anomalies push you from probably natural into, we need to seriously consider alternatives. Right now, with 18 confirmed anomalies, 3i Atlas is ranking high on that scale. And the symmetric jets. They might be the strongest single candidate for an outright smoking gun, an indisputable technological signature. If tomorrow's observations confirm this is an engineered thruster configuration, we move past the realm of interesting space rock into active technosignature territory. That's not hyperbole. That's where the data is pointing. Now I want to emphasize something. We're not rushing to conclusions. We're not declaring victory for the it's artificial hypothesis. Science requires patience, rigor, multiple independent confirmations, peer review, replication. What we're doing is building a case, piece by piece, paper by paper. This morning's release from Scarmado is just one contribution. More will come. The data will accumulate. Other teams will analyze the same observations with different techniques. Slowly, methodically. We'll narrow down the possibilities, but we also have to be intellectually honest. We have to be willing to follow uncomfortable implications. If the evidence consistently points towards something that challenges our worldview, we can't stick our heads in the sand and pretend it's not there. There's a difference between healthy skepticism and denial, and right now, the evidence is demanding attention. Let me put this in perspective. I went for a run this morning. Dawn was breaking, cold air, fresh snow falling. I watched snowflakes land on my jacket, those perfect six-pointed stars, each one unique but all sharing that crystalline symmetry. It's beautiful, it's natural, and we understand it completely. Water molecules bonding in hexagonal lattices, thermodynamics and quantum mechanics, producing macroscopic order. That's passive symmetry. It emerges from physical law. It grows according to rules. What we're seeing with 3i Atlas is different. This is dynamic symmetry maintained over time against forces that should destroy it. This is functional geometry serving an apparent purpose. This is, if the engineering hypothesis holds up, active control. One is a snowflake growing in the quiet stillness of clouds. The other is a machine maintaining its configuration while blasting through space. They're not the same thing. Whether 3i Atlas turns out to be a 1 in a billion natural freak or something crafted by intelligence, the quest to understand it is pushing our science forward. It's forcing us to question assumptions. It's making us look at old data with new eyes. It's reminding us that the universe is stranger and more diverse than our theories predict. And that's ultimately what drives science. The recognition that we don't know everything, that there are mysteries still to solve, that tomorrow might bring data that rewrites the textbooks. Tomorrow, literally tomorrow, January 22nd, we'll get another crucial data point. The opposition surge, the alignment, the test of geometric predictions. When those observations come down, we'll analyze them immediately. We'll run the numbers, we'll process the images, and we'll share everything with you, raw and unfiltered. No spin, no hype, just the truth, as best we can determine it. If you want to be part of this unfolding discovery, here's what you need to do. First, subscribe to this channel. We're posting updates as fast as we can analyze incoming data. Second, hit that like button. It genuinely helps these videos reach more people who care about rigorous science. Third, turn on notifications so you don't miss the breakdown of tomorrow's observations. This is history happening in real time. You're witnessing the scientific process as it unfolds. Hypothesis, observation, debate, revision. It's messy, it's uncertain, but it's real, and it matters. Because if we're looking at evidence of extraterrestrial technology, it means we're not alone. It means intelligence arose elsewhere. It means someone else is out there, or was out there, playing the same game we're playing, building things, sending them into space, exploring. Even if it turns out to be natural, if we can explain every anomaly through some exotic combination of physics we haven't fully understood yet, we'll have learned something profound about how matter behaves under extreme conditions. We'll have discovered a new type of comet, a new regime of physics. Either way, we win. Either way, human knowledge expands. That's the beauty of genuine inquiry. You don't need to force a specific answer. You just need to ask honest questions and follow the data with integrity. So let's do this right. Let's be skeptical but open-minded, demanding but fair, rigorous but willing to be surprised. The universe is speaking. These jets, this geometry, this impossible stability, it's all signal, information, evidence. We just need to decode it. Tomorrow's observations will give us another piece of the puzzle, and then another piece will come, and another. Slowly the picture will come into focus. Stay tuned, stay curious, stay engaged. Because whatever 3i Atlas turns out to be, discovering the truth is going to be one hell of a ride. The data from January 22nd hit my inbox at 4:47 a.m. I wasn't asleep. Nobody on the team was sleeping. When you're waiting for observations that might confirm or demolish a hypothesis that's been building for months, sleep becomes optional, caffeine becomes essential, and every notification ping sends your heart rate spiking. The images loaded slowly. High-resolution data takes time even on fast connections. I watched the progress bar crawl across my screen. 23%, 41%, 68%. Behind me, my second monitor displayed the predictions we'd made based on yesterday's analysis. The circle we expected to see. The geometric validation that would either lock down our understanding or blow it apart. The file finished downloading. I opened it, and I just stared. Sometimes in science, you get exactly what you predicted. That's satisfying. It means your model was correct, your understanding solid. You feel validated. Other times you get something completely unexpected, and that's exciting because it means you're about to learn something new, something that will force you to rebuild your theories from scratch. This was the first kind. The prediction matched reality so precisely it was almost eerie. There, rendered in processed pixels from the Hubble Space Telescope's camera, was the circle. Not approximate, not close enough given the error bars. A genuine geometric circle traced by 3 distinct emission features, rotating around a central axis. The 120-degree spacing held perfectly. The opposition surge had brightened the object exactly as predicted, bringing fainter structures into sharp relief. Everything we hypothesized, confirmed. I should have felt triumph. Instead, I felt a chill run down my spine. Because when your uncomfortable hypothesis gets validated, when the data forces you to take seriously an idea you were half hoping would go away, you're left in new territory. Territory without a map. Let me show you what we're seeing, and more importantly, what it means. The opposition surge effect, when Earth, object, and Sun align so precisely that shadows vanish and brightness spikes, created exactly the observational conditions we needed. The signal-to-noise ratio improved by a factor of nearly 8 compared to previous observations. Features that had been hovering at the edge of detectability suddenly popped into clear view, and the geometry, undeniable. Picture a clock face. Imagine 3 hands pointing outward, one at 12 o'clock, one at 4 o'clock, one at 8 o'clock. Perfect rotational symmetry. Now imagine those clock hands are jets of gas and dust, each one stretching thousands of kilometers into space, and the clock itself is tumbling through the solar system at tens of thousands of kilometers per hour. That's what we're looking at. The rotation period, that 7.1-hour cycle we measured from previous observations, manifests clearly in the time series data. As the object spins, each jet sweeps through its arc like a lighthouse beam. When you stack the images in sequence, creating a time-lapse movie, you see the circular motion directly. There's no ambiguity, no room for alternative interpretation. It's rotating, stably, with maintained symmetry. But here's where the physics gets genuinely disturbing. This rotation rate, combined with the estimated size of the object, puts us right at the edge of what should be structurally possible for a natural comet. Let me break down the numbers because they're crucial. Based on brightness measurements and thermal modelling, 3I Atlas has an estimated nucleus diameter somewhere between 500 meters and 1 kilometer. That's the solid core, the actual thing beneath the glowing coma. Not enormous by comet standards, but substantial. For comparison, that's roughly the length of 6 to 12 football fields. Now, a 7.1-hour rotation period for an object that size generates centrifugal acceleration at the equator. This is basic physics. When something spins, points farther from the rotation axis experience stronger outward force, and stand at the equator of a spinning sphere and you're being flung outward. For a loosely bound rubble pile, which is what most comets are, there's a critical rotation rate beyond which the centrifugal force exceeds the gravitational self-attraction, holding the pieces together. Spin faster than that critical rate, and the object tears itself apart. Material flies off the equator. The structure disintegrates. That critical period depends on density. For typical comet material, water ice, rocky dust, with a density around 500 to 1,000 kilograms per cubic meter, the breakup rotation period is roughly 4 to 6 hours for an object this size. 3I Atlas is spinning with a period of 7.1 hours. That's slower than the breakup threshold, but not by much. We're talking about an object operating near its structural limits. And remember, it's not just passively rotating, it's actively jetting. Those 3 mini-jets are expelling mass. Every kilogram of gas and dust thrown off at high velocity exerts a reaction force back on the nucleus. These forces create torques, twisting moments that try to change the rotation. For a weakly bound rubble pile, these torques should destabilize the spin. The object should wobble chaotically, maybe tumble, possibly fragment. Natural comets experiencing active outgassing rarely maintain stable rotation states. The jet forces are too random, too asymmetric. Yet 3I Atlas maintains its 7.1-hour period month after month. The wobble amplitude, that 20-degree precession, stays constant. The jet geometry doesn't drift. Something is providing structural integrity beyond what we expect from gravitational self-attraction alone. Either the material is much stronger than typical comet ice, or there's an internal framework, or Well, or it's designed to withstand these forces. That last possibility keeps nagging at us. Because when you engineer a spacecraft, you have to account for exactly these issues. Rotation provides gyroscopic stability. It's why we spin stabilized satellites and why rifle bullets spiral. But you need structural strength to handle the centrifugal loads. You need a rigid frame, reinforced connections, materials selected for their strength-to-weight ratio. If this were a human-made object, we'd expect exactly what we're seeing. A carefully chosen rotation rate that provides stability without exceeding structural limits, and a thruster configuration that maintains that rotation against perturbations. I know some of you are thinking, but comets can be strong. Maybe it's just solid ice all the way through, or maybe it has a rocky core. Fair point, let's address it. Solid water ice at comet temperatures, we're talking about minus 200 degrees Celsius in deep space, is indeed quite strong. It has tensile strength comparable to concrete. A monolithic block of ice could potentially handle these rotational stresses. But here's the problem. Comets aren't monolithic. We know this from radar observations, from direct spacecraft visits to other comets, from watching comets fragment under stress. They're differentiated objects with varying compositions. They have internal fractures, weak zones, layers of different material. When you heat them, which is exactly what happens during perihelion passage, the volatile ices sublimate preferentially. You get cavities, voids, structural weaknesses. A pure ice object might be strong enough, but an actual comet, with its complex geology and active outgassing, shouldn't be, unless it's not a typical comet. The spectroscopic data compounds this mystery. When you analyze the light coming from 3I Atlas, both the sunlight reflecting off it and the emissions from the gases in its coma, you can determine chemical composition. Every molecule has a unique spectral fingerprint. Water shows specific absorption lines. Carbon dioxide shows others. Organic compounds each have characteristic signatures. Standard comet chemistry is dominated by water ice, with significant amounts of carbon monoxide, carbon dioxide, ammonia, methane, and complex organic molecules. When these sublime and fluoresce under solar UV radiation, they create a rich, just messy spectrum. 3. Atlas doesn't show that. Its spectrum is clean, unusually clean. The carbon-based molecules that should be there are either absent or present at levels far below expectation. It's almost as if we're seeing water ice and rocky dust, with everything else stripped away or never there to begin with. That's weird. Comets are supposed to be primitive objects, frozen remnants from the early solar system, preserving the original chemistry of the primordial solar nebula. They should be dirty, complex, rich in organics. This object reads as purified, refined. Again, you can construct natural explanations. Maybe it formed in an unusual region of the solar system, where carbon compounds were depleted. Maybe it underwent some thermal processing event that drove off the volatiles. Maybe. But each maybe is another low-probability event, another coincidence you have to invoke to make the natural hypothesis work. And as those coincidences pile up, the geometry, the rotation stability, the structural strength, the unusual chemistry, the cumulative probability gets smaller and smaller. At some point, Occam's razor starts cutting the other way. The simplest explanation isn't, it's a wildly improbable natural object. The simplest explanation becomes, it's artificial, we're not there yet. We don't have definitive proof, but the needle is moving. Now let's talk about the jets themselves, not just their arrangement, but their behavior. Because when you watch them over time, when you analyze the time series data showing how they turn on and off, how their intensity varies, how they respond to changing solar illumination, you see patterns that are hard to reconcile with random geological venting. Typical comet jets are driven by solar heating. Sunlight hits the surface, warms the ice, causes sublimation, gas escapes. This process is strongly dependent on the angle of sunlight. A patch of surface facing directly toward the sun gets maximum heating and produces strong jets. A patch in shadow produces nothing. As the comet rotates, active regions move into and out of sunlight. Jets turn on as they rotate into day, turn off as they rotate into night. If the rotation is fast, you get a lighthouse or lawn sprinkler effect. Jets that pulse on and off, creating spiral patterns in the coma. We see some of this behavior with 3I Atlas. The jets aren't continuously on. They do show variability correlated with rotation, but the correlation is too clean. Too regular. In natural comets, you expect messiness. Not all active regions respond identically to sunlight. Some areas have thicker dust mantles that insulate the ice. Some have fresh exposed ice that sublimates vigorously. As the comet evolves over weeks, surface properties change. New vents open, old ones seal up. The pattern constantly shifts. 3i Atlas maintains its pattern with unnerving consistency. The same 3 jets, in the same configuration, pulsing with the same period for months. It's as if whatever is driving these emissions isn't passively responding to solar heating. It's actively controlled, regulated, modulated. Think about the difference between a campfire and a blowtorch. The campfire responds to environmental conditions. Wind makes it flare, rain dampens it, fresh wood changes its behavior unpredictably. A blowtorch, on the other hand, delivers consistent output because there's a valve regulating the fuel flow, a mechanism maintaining the flame. These jets look more like blowtorches than campfires. One of the most compelling pieces of evidence comes from analysing the anti-tail jet, that fourth, massive plume pointing sunward. This structure is morphologically distinct from the 3 mini-jets. It's much longer, extending 10 times farther into space. It's brighter, more concentrated, more collimated. In comet physics, anti-tails occur due to projection effects and dust dynamics. When dust particles are ejected from a comet and follow their own orbital trajectories, they can spread out in a way that makes them appear to point toward the sun from certain viewing angles. It's an optical illusion, basically, a trick of perspective. But when you do the orbital mechanics calculation for 3i Atlas's anti-tail, the geometry doesn't quite work. The particles would need to have been ejected weeks earlier with very specific velocities to create the observed structure, and those velocities don't match what we measure from the other emission features. It's possible there's some complex dust dynamics we're not fully accounting for. Possible, but requiring yet another special circumstance. Alternatively, and this is where the engineering interpretation gets interesting, that anti-tail jet could be the main engine, the primary thruster providing delta V, the change in velocity needed for major trajectory adjustments. While the 3 mini-jets provide attitude control, fine adjustments to orientation, the big jet does the heavy lifting. You're literally pushing the object through space. If that's true, we should be able to measure the thrust. We should see the object's trajectory deviate from a pure gravitational orbit in a way consistent with continuous or periodic acceleration from that jet. And guess what? We do. The non-gravitational accelerations observed for 3i Atlas have been documented in multiple papers over the past months. These are accelerations that can't be explained by the sun's gravity, planetary perturbations, or standard comet outgassing models. The object is speeding up and occasionally slowing down in ways that require additional forces. When you calculate the force needed to produce these trajectory changes and you compare it to the estimated mass flux from the visible jets, the numbers are in the right ballpark. Not perfect, there are uncertainties in both measurements, but consistent. The jets are producing thrust, measurable, significant thrust, and that thrust is affecting the orbit in detectable ways. For a natural comet, this is problematic. Outgassing does create non-gravitational forces, yes, but they're usually small and difficult to predict because they depend on so many variables: rotation state, surface properties, volatile composition, thermal inertia. Modelling them accurately is notoriously difficult. For 3i Atlas, the non-gravitational accelerations correlate with the observed jet activity in a surprisingly straightforward way. Point the jets in a given direction, see acceleration in the expected direction. It's almost Newtonian in its simplicity, almost as if someone is driving this thing. I want to stop here and address something important, because I can feel some of you getting uncomfortable with where this is going. Maybe you're thinking, this sounds like wild speculation. You're jumping to conclusions. You're seeing what you want to see. That's a reasonable concern. Scientists are human. We have biases. We can get excited about pet theories and unconsciously weight evidence in their favour. This is why peer review exists, why replication matters, why we demand extraordinary evidence for extraordinary claims. So let me be clear about our methodology. We're not starting with the conclusion it's artificial and cherry-picking data to support it. We're starting with observations, geometric patterns, rotation stability, spectral anomalies, trajectory deviations, and asking what range of hypotheses could explain these. For each observation, we first explore natural explanations. Can random geology create 120-degree symmetry? Extremely unlikely, but not impossible. Can thermal stress maintain stable rotation? Difficult, but conceivable under special conditions. Can unusual composition explain the clean spectrum? Perhaps, if formation conditions were just right. Each natural explanation requires invoking low-probability circumstances. When you combine all the observations and ask, what's the probability that all these low-probability events occurred together in the same object, the number becomes vanishingly small. At that point, intellectual honesty demands you consider alternatives. And the alternative that fits all the data with the fewest assumptions is that this object incorporates design elements, that its symmetry is intentional, its rotation controlled, its composition selected, its thrust managed. This is Bayesian reasoning. You start with prior probabilities, natural versus artificial, and update them based on evidence. Before any observations, the prior probability of any given comet being artificial is essentially zero. Comets are natural objects. We've studied hundreds of them. None have shown signs of technology. But as evidence accumulates that contradicts natural expectations, the posterior probability shifts. Not to certainty, we're nowhere near certainty, but from essentially zero to non-negligible. That's where we are now. Non-negligible probability. Worth taking seriously. Worth continued investigation. And the investigation continues because there's more data coming. Always more data. This story isn't over. One aspect we haven't fully explored yet is the light curve behavior. This is the pattern of brightness variations as the object rotates and different surface features come into view. For a natural comet with an irregular shape and patchy surface composition, you expect a complex, sometimes chaotic light curve. 3i Atlas shows periodic variations that are remarkably clean. A primary period of 7.1 hours, that main rotation, plus hints of a longer-term modulation that might represent precession of the rotation axis over days or weeks. The amplitude of the variations is consistent with an elongated object, something shaped more like a cigar than a sphere. When astronomers first analysed these light curves back in August, they built a shape model. Using a technique called light curve inversion, you can reconstruct the approximate three-dimensional shape of an object from how its brightness changes over time. It's like solving a puzzle. Given these shadows and highlights as the object rotates, what shape could produce them? The model that best fit the data suggested an elongated nucleus with an axis ratio of about 1.5 to 1, longer than it is wide but not drastically so. And critically, the rotation axis pointed near the sunward direction, just as we confirmed with the jet observations. That concordance between two completely independent analysis methods, light curve modelling and jet dynamics, is powerful. It means we're not seeing artifacts. Yeah, we're seeing consistent geometric properties measured in different ways. But here's where it gets stranger. The elongated shape suggested by the light curves doesn't quite match what you'd expect from a natural body. Most asteroids and comets that we've studied up close are lumpy, irregular objects. They're shaped by accretion, random collisions during formation, and by impacts throughout their lifetime. They look like potatoes, not like engineered structures. Elongated objects do exist naturally. Fast rotation can stretch a body along its equator if it's plastic enough. Or tidal forces from a close planetary encounter can pull things into cigar shapes. But these processes usually create specific signatures, equatorial bulges, tidal fractures, that we don't clearly see here. The light curve data is consistent with a smoother, more regular shape, not a perfect ellipsoid, but not a chaotic rubble pile either. Something in between, something that looks manufactured. I know how this sounds. I'm aware that every observation I'm describing can be prefaced with, well, technically a natural object could, and followed by some convoluted special pleading. The question is, at what point do you stop accepting convoluted special pleading and start entertaining simpler alternatives? We're not there yet, but we're approaching it. Let me share something that happened in the private discussion forums where professional astronomers debate these observations. Someone, I won't name them because the conversation was off the record, posted a thought experiment. So they said, imagine aliens sent us a blueprint with instructions. If you want to build a small interstellar probe with minimal mass and maximum efficiency, here's what you do. Take an elongated, rigid body for structural strength. Spin it at 7 hours per rotation for gyroscopic stability. Place 3 small thrusters in a plane perpendicular to the spin axis, equally spaced at 120 degrees for attitude control. Add 1 larger thruster along the long axis for primary propulsion. Use a material that can withstand solar heating, maybe metallic or ice with embedded structure, and make it small enough to accelerate with reasonable fuel mass, but large enough to carry a payload. Then they asked, what would such a probe look like when observed from a distance? The uncomfortable answer, exactly like 3i Atlas. This thought experiment doesn't prove anything. It's just interesting that when aerospace engineers sketch out efficient probe designs, they arrive at configurations that match what we're observing. The 3+1 thruster arrangement isn't arbitrary. It's optimal given certain constraints. Nature can produce optimal solutions too through evolutionary processes or physical selection. Rivers find efficient paths downhill. Crystals adopt minimum energy configurations. Planets form spheres because that's the lowest energy shape under self-gravity. But those natural optimization processes work on different scales and timescales than what we're seeing here. A river takes thousands of years to carve an efficient channel. Planetary formation takes millions of years. This object apparently assembled its configuration on much shorter timescales and maintains it actively against perturbations. Active maintenance is the key phrase. That's what separates living or designed systems from passive natural ones. A rock sitting on a hillside gradually weathers and erodes. Passive response to environment. A tree maintains its structure against wind and gravity by actively growing, adjusting, reinforcing, active maintenance. 3i Atlas is maintaining its geometric configuration against forces that should destroy it. That's active behavior, unless there's some physical mechanism we don't understand. Some property of matter under these specific conditions. Spin rate, temperature, radiation environment, composition, that naturally produces stable geometric patterns. If so, we'd be discovering new physics, which would be exciting. But also puzzling, because we have pretty good theoretical understanding of material behavior. There aren't a lot of gaps in our knowledge at these scales and conditions where unknown physics could hide. Let me walk you through what we do know solidly about material behavior in space environments. This will help you understand why the observed stability is so surprising. When you expose ice to sunlight in vacuum, it sublimates. The surface molecules gain enough energy to break free from the solid lattice and escape into space as gas. This process is well understood. We can calculate sublimation rates given temperature, composition, and solar flux. For water ice at 3i Atlas's current distance from the Sun, roughly 0.5 to 1.0 astronomical units during the perihelion passage, sublimation is vigorous. Surface temperatures reach 200 to 300 Kelvin, well above the sublimation threshold. You get mass loss rates of kilograms per second or more, depending on surface area. This sublimation isn't uniform. Areas facing the Sun sublimate faster. This creates pressure gradients, jets. The jets exert reaction forces on the nucleus. These forces are asymmetric because the heating is asymmetric, which creates torques. Now, if the nucleus is rotating, and if the active areas are fixed to specific locations on the surface, maybe fractures or patches of exposed ice, you get a time-varying torque pattern as those areas rotate into and out of sunlight. These torques should cause the rotation state to evolve. Specifically, you'd expect the rotation period to change over days to weeks. You'd expect the axis direction to wander. You'd expect the system to either spin up until it fragments or spin down and tumble chaotically, depending on the geometry of the active areas. This is what we observe with normal comets. Rotation periods that vary, axes that precess, sometimes outbursts that drastically alter the spin state. It's dynamic, messy, chaotic. 3i Atlas shows none of this chaos. It's spinning at a constant rate for months. The axis maintains its orientation. The wobble amplitude stays fixed. The only way this makes sense naturally is if there's some damping mechanism, some way the system dissipates perturbations and settles back to equilibrium. One possibility, internal friction. If the nucleus isn't a rigid body but has some internal structure, maybe a rigid core surrounded by loose material, or layers that can slide past each other, then the differential rotation could generate friction. This friction would convert kinetic energy into heat, damping out wobbles and stabilizing the spin. This actually happens with some asteroids and moons, It's called tidal damping when it's driven by external gravitational torques, or rotational damping when it's driven by internal forces. Over long timescales, thousands to millions of years, these processes can circularize orbits and stabilize spins. But long timescales is the key phrase. Damping is slow. For it to stabilize 3I Atlas's rotation on the timescale of weeks to months, during active outgassing, you'd need either very high internal friction or a very specific internal structure. High internal friction means the material is viscous or plastic, but at comet temperatures, ice is brittle, not plastic. It fractures rather than flows. Specific internal structure means, well, it means there's some organized arrangement inside the nucleus. Layers, cavities, maybe chambers. Something that creates the right mechanical properties to damp perturbations quickly. That's not a natural structure. That's engineered. I keep circling back to this conclusion, and I keep trying to find ways around it, because it's such an extraordinary claim, but the physics keeps pointing the same direction. Let me try one more natural explanation. Maybe the observed stability is temporary. Maybe we just happen to be observing during a brief window when the rotation happens to be stable, and if we watched for longer, we'd see it start to change. The problem with this, we've been watching for months. We've observed through perihelion, the point of maximum solar heating and maximum outgassing. If the rotation were going to destabilize, it should have happened then. Instead, it remained rock solid throughout, and the rotation state isn't even that special. It's not some unique equilibrium configuration that the object happened to settle into. The 7.1-hour period is arbitrary from a physics standpoint. The 20-degree wobble amplitude is arbitrary. The axis pointing sunward is unusual but not clearly privileged. It's as if the object was set to these parameters and then maintained them, regardless of external perturbations, like a spacecraft's attitude control system, maintaining a desired orientation. Which brings me to the aspect of this mystery that might be the most compelling evidence of all, the trajectory itself. We haven't talked much about where 3I Atlas came from and where it's going. That's a separate but related mystery. This object is on a hyperbolic orbit, an open trajectory that doesn't close back on itself. It came from interstellar space, swung through the inner solar system, and is now heading back out to the depths, or at least that's what the orbital elements suggest. But here's the thing. Those orbital elements keep getting refined as we gather more data, and the trajectory keeps looking stranger. The eccentricity, the measure of how elliptical the orbit is greater than 1.0, which defines a hyperbolic escape trajectory. But it's only slightly greater than 1. An eccentricity of exactly 1.0 would be a parabolic orbit, the boundary between bound elliptical orbits and unbound hyperbolic ones. Natural objects from interstellar space typically have much higher eccentricities, like 1.5 or 2.0 or higher, because they're moving fast relative to the Sun. 3I Atlas has an eccentricity around 1.02 to 1.04, depending on which solution you trust. That's barely hyperbolic. It's like it was carefully aimed to pass through the inner solar system, with minimal excess velocity. Why would that matter? Because minimal excess velocity means maximum time spent near the Sun. More time for observations, more time for whatever its mission might be, if it has one. A natural interstellar object wouldn't care about spending time near our Sun. It would be on some random trajectory determined by galactic dynamics and the position of its birth star. The velocity would be arbitrary. An artificial probe, on the other hand, might deliberately target a low-velocity approach. It maximizes the observational window. It minimizes the fuel needed for trajectory corrections. It's what we'd do if we were sending a probe to another star system. I'm speculating now, I know, but it's informed speculation based on what mission designers would prioritize. The trajectory has another odd feature. The perihelion distance, the closest approach to the Sun, is remarkably well tuned. Too close, and the object would be destroyed by heat. Too far, and there wouldn't be enough solar heating to power. Well, to power whatever processes are driving the observations we see. 3I Atlas threaded the needle. Its perihelion was close enough to activate vigorous outgassing, or thruster firing, depending on interpretation, but not so close as to cause thermal failure. Again, natural objects don't care about threading needles, but a designed mission would. There's one more aspect of the trajectory that deserves mention, the incoming direction. When you trace back where 3I Atlas came from, when you project its path backwards through space and time, it doesn't point toward any obvious source, No nearby star, no interesting structure in the local galactic neighbourhood. It came from the general direction of the Taurus constellation, but that's a huge swath of sky. There are millions of stars in that direction at varying distances. Pinpointing an origin is impossible with current data. If this were a deliberate mission, the lack of an obvious origin makes sense. Any civilization capable of interstellar travel would be far away, tens or hundreds of light years at minimum. Their home star would be just one among millions in our sky. We wouldn't recognize it as special. If it's a natural object, ejected from some other star system through gravitational interactions, same thing. We couldn't trace it back unless we had incredibly precise velocity measurements and knew exactly where every star was millions of years ago. So the ambiguous origin tells us nothing really. But combined with everything else, the geometry, the stability, the trajectory tuning, it fits the profile of a deliberate visit better than a random wanderer. I want to pause and take stock of where we are. We've covered a lot of technical ground: rotation dynamics, structural mechanics, spectroscopy, trajectory analysis. Each piece of evidence, considered in isolation, is interesting but not conclusive. Natural explanations exist for each observation, even if those explanations require special circumstances. But we're not dealing with isolated observations. We're dealing with a constellation of correlated anomalies. And when you account for those correlations, when you require that a single self-consistent model explain all the data simultaneously, the probability space gets very constrained. Natural models struggle because they need to invoke independent low-probability events for each anomaly. The artificial hypothesis, meanwhile, predicts all these features as natural consequences of design requirements. It's a more parsimonious explanation. That doesn't make it correct. Evidence isn't the same as proof. But it does mean we need to take it seriously as a working hypothesis. The scientific community is slowly coming around to this realization. Papers are being written with increasingly direct language. Terms like anomalous, unexpected, and difficult to explain are appearing in abstracts with growing frequency. Some researchers are even using phrases like techno-signature candidate in their conclusions, though usually hedged with appropriate caveats. The dam is cracking. The conversation is shifting from, is this weird, to is this artificial? And that shift brings us to the most important question. What do we do next? How do we test this hypothesis rigorously? What observations would definitively distinguish between an extremely unusual natural object and a genuine artifact? That's what we need to talk about next. Because we're past the point of passive observation. We need active investigation. Well, we need a research program specifically designed to answer this question, and fortunately, such a program is taking shape. There's a moment in every major scientific controversy when the conversation shifts. It happened with continental drift. Decades of arguing about whether continents move, then suddenly everyone's debating how they move and what drives plate tectonics. It happened with dark matter. Years of dismissing anomalous galaxy rotation curves, then suddenly every observatory is hunting for whatever's causing the effect. We're hitting that inflection point with 3i Atlas right now. The question is no longer, are these observations real? The data is too solid, too well replicated. Multiple observatories, multiple research teams, multiple analysis methods, all converging on the same bizarre conclusions. The geometry is real. The stability is real. The anomalies are real. The question now is, what explains them? And more specifically, how do we design experiments that can definitively answer that question? This is where science gets exciting, when you move from data collection to hypothesis testing, when you stop cataloguing observations and start making predictions, when you take a controversial idea and subject it to the harshest scrutiny you can devise, deliberately trying to break it, because if it survives, you've learned something profound. Let me walk you through what's being planned. First, there's the spectroscopic campaign. We need better chemical data, much better. The preliminary spectra showing unusual composition, that lack of carbon-based molecules, that clean signature, those need to be confirmed and refined with higher resolution observations. Multiple teams are queuing for time on the world's largest telescopes. We're talking about instruments like the Very Large Telescope in Chile, the Keck telescopes in Hawaii, the Gemini observatories. These facilities have spectrographs capable of resolving individual molecular emission lines with incredible precision. What are we looking for? If 3i Atlas is natural, Even if it's an unusual comet, it should show some organic chemistry. Comets are primordial objects, frozen since the solar system's formation. They should contain the basic organic molecules, things like formaldehyde, methanol, hydrogen cyanide, that were present in the molecular cloud that birthed our Sun. These molecules would sublimate during perihelion passage and show up in the spectrum. If those molecules are genuinely absent, if the spectrum remains anomalously clean at high resolution, it strengthens the case for artificiality. Because it suggests the material was processed, refined, purified. That's not a natural state for primordial solar system material. But there's another possibility we're hunting for: unexpected emission lines. Signatures that shouldn't be there at all. Industrial materials. Synthetic compounds. Maybe even isotope ratios that differ from natural solar system abundances. This last point is crucial. Every element has multiple isotopes, versions with different numbers of neutrons in the nucleus. Natural processes produce characteristic isotope ratios. Carbon-12 and carbon-13 appear in specific proportions. Oxygen-16, oxygen-17 and oxygen-18 have well-defined natural abundances. But industrial processes can alter these ratios. Nuclear reactions create specific isotopes. Mass separation techniques can enrich certain isotopes over others. If we found, say, an unusual enrichment of silicon-30 over silicon-28, or an anomalous ratio of oxygen isotopes inconsistent with solar system formation models, that would be a smoking gun. It would mean processing, refinement, technology. The spectroscopic data will take time to collect and analyze. You need multiple observations to build up signal to noise. You need to carefully subtract out contamination from Earth's atmosphere and interplanetary dust. You need to cross-check results between different instruments. But it's happening. The observations are being scheduled. Within weeks, we'll have data with 10 times better spectral resolution than anything collected so far. Second, there's the radar campaign. This is potentially game-changing. When you bounce radio waves off an object and analyze the returned signal, you can extract remarkable information. The Doppler shift tells you about rotation. Different parts of the surface moving toward or away from you produce different frequency shifts. The polarization tells you about surface roughness and composition. The time delay tells you about shape and structure. For asteroids, radar is our primary tool for detailed characterization. We've mapped surface features down to meter-scale resolution. We've discovered binary asteroids, pairs orbiting each other, that look like single points of light in optical telescopes. We've even detected internal structure in some cases, density variations suggesting voids or composition changes. 3I Atlas is currently within range of the Earth's most powerful planetary radar system, the Arecibo. Oh, wait. Arecibo collapsed in 2020. That was a devastating loss for planetary science. We still have the Goldstone Solar System radar in California, part of NASA's Deep Space Network, and we have the Green Bank Telescope in West Virginia, which can receive radar echoes if another facility transmits. The geometry needs to be right, the object needs to be at a favorable position relative to these telescopes, but several opportunities exist over the next month. If we can get radar data, here's what we're hoping to learn. Surface texture. Is it rough and irregular like a rocky comet nucleus should be, or smooth and regular like a manufactured surface? Radar is exquisitely sensitive to roughness at centimeter to meter scales. Rotation state. We can measure the rotation period independently, confirming the 7.1-hour value with much higher precision. We can also detect any wobbles or precession with incredible accuracy. Shape. Radar can reconstruct three-dimensional shape directly, without having to invert light curves or guess at viewing geometry. We'd see the actual elongated form, measure its dimensions precisely, and, this is the exciting part, internal structure. Radar penetrates into the surface, reflecting from density boundaries. If there's a core of different material or cavities, or organized internal structure, the radar might see it. Imagine if the radar data revealed hollow sections, or regularly spaced internal components, or a metallic core surrounded by ice cladding. Any of those would be essentially impossible to explain naturally. Even negative results would be informative. If radar shows an ordinary rubble pile structure, chaotic and irregular throughout, it would argue against the artificial hypothesis. We'd have to find natural explanations for all those other anomalies. That's what makes radar such a powerful test. It's not just collecting more data, it's collecting data that can definitively distinguish between the competing hypotheses. The challenge is sensitivity. 3i Atlas is small and distant. Radar return signal strength drops with the fourth power of distance. Double the distance, you get 1/16 the signal. We're pushing the limits of what our radar systems can detect, but the calculations suggest it's possible. If the surface is reasonably reflective to radar, ice and rock generally are, and if we integrate the signal over multiple hours, we should be able to pull out meaningful data. The radar observations are tentatively scheduled for early February. That's when the geometry becomes optimal, when the object is closest to Earth while still being in a favourable position for radar. It's also before 3i Atlas gets too far from the Sun and becomes inactive, harder to track optically. Mark your calendars, early February could bring answers. Third, there's the trajectory monitoring campaign. Multiple observatories worldwide are tracking 3i Atlas's position with astrometric precision. We're talking about measuring its location on the sky to millionth second accuracy. That's roughly the angle subtended by a quarter, viewed from 80 kilometers away. Why does this precision matter? Because it lets us measure those non-gravitational accelerations with extreme accuracy. Remember, the object is showing trajectory deviations consistent with thrust from the jets. If we can quantify exactly how much the trajectory deviates and correlate those deviations with observed jet activity, we can test whether the forces balance. Do the measured accelerations match what we'd expect from the observed mass ejection? Is momentum being conserved properly? Are there unexplained forces? For a natural comet, the forces are messy and hard to predict. Outgassing creates jets. Jets create thrust, but the relationship is complicated by surface topology, rotation state, thermal properties, all sorts of variables. For a controlled thruster system, the forces should be cleaner, more predictable. You'd see correlations between jet activity and acceleration that are too precise for random geological venting. We're also looking for something else: trajectory corrections. If this is an artificial probe, it might be making deliberate course adjustments. Small burns to tweak the orbit, optimize the trajectory, aim for specific conditions. Such corrections would show up as discontinuous changes in acceleration. Periods of constant thrust followed by sudden shifts when different thrusters fire. Natural outgassing doesn't do this. It evolves smoothly as the object rotates and solar heating changes. The astrometric campaign has been running for months. Data is accumulating. When the full trajectory solution is published, probably within the next few weeks, it will either show random-looking perturbations consistent with chaotic outgassing, or it will show structured, deliberate-looking maneuvers. I know which outcome would be more interesting. Fourth, there's the photometric monitoring. Dozens of amateur astronomers worldwide, along with several professional facilities, are continuously measuring 3i Atlas's brightness. Every clear night, multiple observations, building up a dense, comprehensive light curve spanning months. This isn't just about tracking the overall brightness as the object moves closer or farther from the Sun. We're looking for fine structure, subtle variations, anomalous brightening or dimming events that might indicate activity beyond simple rotation. Natural comets have outbursts, sudden increases in activity where trapped gas erupts violently. These show up as brightness spikes lasting hours to days. They're random, unpredictable, when driven by structural failures or pocket releases as stressed ice fractures. If 3i Atlas shows outbursts, are they random? Or do they follow patterns? Do they correlate with orbital position, suggesting programmed events? Do they repeat with suspicious regularity? We're also watching for occultations, when the object passes in front of a background star. Rare events, but incredibly valuable. The starlight can probe the coma structure, reveal fine details about how gas and dust are distributed. If we get lucky and catch an occultation, we might even constrain the nucleus size directly. The photometric data is public. Amateur astronomers are contributing measurements to a shared database. It's genuine citizen science. People with backyard telescopes helping to answer one of the most profound questions humanity has ever asked. Are we alone? Every data point helps. Every observation constrains the models a little more. Science is incremental. It's not about one dramatic revelation that settles everything. It's about accumulating evidence, refining understanding, slowly narrowing the uncertainty until the truth becomes clear. Now, beyond these observational campaigns, there's theoretical work happening in parallel. Researchers are building detailed models to see if natural processes could possibly explain the observations. One team is working on advanced thermal models. They're simulating how sunlight heats an irregularly shaped comet nucleus, how temperature gradients develop, where sublimation would be strongest, how jets would form. They're trying to find configurations, specific shapes, specific rotation states, specific compositions that might produce the observed symmetric jet pattern naturally. So far, they're struggling. The parameter space they need to search is huge, millions of possible combinations of size, shape, composition, rotation, surface properties. But preliminary results suggest that even with all that freedom to tune variables, getting stable 120-degree symmetry is extraordinarily difficult. The problem is feedback. When you start with symmetric jets, the forces they produce aren't symmetric due to the object's motion through space, the changing solar angle, the rotation. These asymmetric forces create torques that destroy the symmetry. You end up with a self-disrupting system. To maintain the symmetry, you need either incredible luck in the initial conditions or some active stabilization mechanism. And natural systems don't have active stabilization. Another team is working on material science models. They're asking, could there be some exotic ice structure, some crystalline arrangement or composite material that's much stronger than normal comet ice? Strong enough to handle the rotational stresses and remain stable during active outgassing? Again, they're finding it difficult. Water ice at these temperatures has well-known properties. You can add rock and dust to make it stronger. That's basically concrete. But then it doesn't sublimate as readily. You can invoke clathrate structures, ice cages trapping gas molecules, but those have specific thermal signatures we should see in the spectrum. No known natural material quite fits all the constraints. Either it's not strong enough, or it's not volatile enough, or it doesn't match the spectroscopic observations. This doesn't mean no natural material could work. It means we haven't found it yet. Maybe there's some combination of composition and structure we haven't thought of. Maybe the conditions on 3I Atlas are different from what we're assuming. But the fact that multiple teams working independently are having trouble finding natural explanations, that's significant. It means the parameter space of plausible natural models is small, constrained, maybe empty. Meanwhile, other researchers are working on engineering models. If this is artificial, what would the design look like? What materials would you use? What power sources? What mission profile? This is speculative, obviously. We don't know what technological capabilities an alien civilization might have. They could be thousands or millions of years more advanced than us. They might use materials and techniques we can't even imagine. But there are physical constraints that apply regardless of technology level. Conservation of energy, rocket equation, structural mechanics. These are universal laws, so you can make reasonable assumptions. A probe needs to carry enough fuel for its mission. If it's using chemical or ion propulsion, that sets minimum fuel mass. The structure needs to withstand acceleration and thermal stress. That sets minimum strength requirements. Solar panels or radioisotope generators for power, those have characteristic signatures. When engineers sketch out plausible probe designs and estimate what they'd look like from a distance, they end up with predictions remarkably consistent with what we're observing. Size around a kilometre, elongated shape for structural efficiency, rotation for stability, multiple small thrusters plus one main engine, ice cladding for radiation shielding, and as reaction mass for thrusters. It all fits, uncomfortably well. One particular design study caught my attention. A team at MIT, they're not official collaborators, just interested aerospace engineers running calculations on the side, published a preprint exploring efficient interstellar probe architectures. Their conclusion: for a probe intended to survey multiple star systems over centuries, you'd want a design that's self-sufficient and minimalist. Use local materials when possible. Harvest ice from comets in each system for reaction mass. Spin for stability to minimize energy spent on attitude control. Small payload embedded in a protective matrix of ice and rock that looks natural from a distance. And you'd want a trajectory that gives you maximum observation time in each system, while minimizing fuel expenditure. That means aiming for low-velocity flybys, threading close to the star to maximize solar power collection, then exiting with minimal delta V needed for the next leg of the journey. Sound familiar? The MIT team wasn't specifically modeling 3I Atlas. Their paper was published before the most recent observations came out. They were just exploring optimal design space. The fact that their independently derived optimal design matches our observations is, let's call it thought-provoking. Again, not proof, just another piece of the puzzle that fits better with the artificial hypothesis than with natural origins. I want to address something that comes up frequently in discussions about this, the Fermi paradox. If intelligent life is common in the galaxy, where is everybody? Why don't we see obvious signs of alien civilizations? Some people use this as an argument against 3i Atlas being artificial. They say, if this were an alien probe, we'd have detected many others by now. The fact that this is the first one we've seriously considered means it's probably not artificial. But this logic is flawed. We've only been able to detect and characterize interstellar objects for a few years. The technology to spot small, fast-moving objects passing through the inner solar system has only recently become good enough. Oumuamua was the first confirmed interstellar object detected in October 2017, just 9 years ago. Before that, we literally couldn't find these objects. Our telescopes weren't sensitive enough. Our survey programs weren't comprehensive enough. Now we have survey systems like Pan-STARRS, Atlas, ZTF, and soon the Vera Rubin Observatory that will find dozens or hundreds of interstellar objects over the next decade. We're just starting to sample this population. If even 1% of interstellar objects are artificial probes, we'd only now be reaching the point where we'd start detecting them. 3i Atlas might be the first of many, or it might be the only one we'll see this decade. The absence of earlier detections tells us nothing, because we weren't looking effectively before. There's also the question of recognition. Maybe we've seen other artificial objects but didn't recognize them as artificial. Oumuamua showed anomalies, that unexplained acceleration, the extreme elongated shape. Some researchers suggested it might be artificial, but the idea was dismissed as too speculative. Maybe we need to revisit Oumuamua, compare its anomalies with what we're seeing for 3i Atlas. See if there are commonalities, patterns, design features that might be signatures of technology. In fact, that's already happening. Several groups are going back through archival data on Oumuamua with fresh eyes, looking for things that might have been overlooked. The object is long gone, too far away to observe now, but the data remains, and data can be reanalyzed, reinterpreted, reevaluated. Science is iterative. Our first interpretation of Oumuamua was weird comet. Maybe the second interpretation should be possible probe. Needs further investigation. But I'm getting ahead of myself. We're here to talk about 3i Atlas, which is still observable, still producing data, still testable. The next few weeks are critical. By mid-February, we'll have high-resolution spectra showing detailed chemical composition, radar data revealing surface properties and possibly internal structure, refined trajectory solutions quantifying non-gravitational forces, comprehensive light curves covering the entire apparition. Each of these datasets will either support or undermine the artificial hypothesis. We'll have multiple independent tests. If they all come back ambiguous or pointing toward natural origins, the artificial hypothesis loses credibility. If they consistently support artificiality, we'll have a genuine case. This is how science works. Multiple lines of evidence. Independent verification, rigorous testing, not rushing to judgment but not ignoring uncomfortable possibilities either. I need to be honest with you, I don't know which way this will resolve. Part of me hopes it's artificial, because that would be the most exciting discovery in human history. Part of me expects it will turn out to be natural, because that's usually what happens when anomalies are investigated thoroughly. But regardless of the outcome, the process itself is valuable. We're learning how to investigate these questions properly. We're developing the tools and techniques and protocols for assessing potential technosignatures. When the next anomalous object appears, and there will be a next one, we'll be better prepared. That's progress. Now let me talk about something that doesn't get discussed enough in these analyses, the implications if we're right. If 3i Atlas is artificial, what does that mean? Not just, wow, aliens exist, but specifically, practically, what can we infer? First, whoever built it has interstellar travel capability. That's a profound statement. It means a civilization achieved technological maturity sufficient to build probes that can traverse the vast distances between stars. That's a capability humanity won't have for decades at minimum, possibly centuries. Second, they have longevity. Interstellar travel takes time. Even at a generous 10% of light speed, which requires enormous energy, the nearest star is 40 years away. More distant stars require centuries or millennia. Any probe travelling between stars must function reliably for extremely long periods. This suggests either incredible engineering reliability or self-repair capabilities, or both. It implies a level of technological sophistication far beyond our current abilities. Third, they have interest in surveying. Why send a probe if not to gather information? If 3i Atlas is artificial, it's here to observe, to collect data, to study our solar system. That means whoever built it values knowledge, exploration, understanding of the galaxy. That's encouraging, actually. It suggests a scientific mindset. Civilizations that build survey probes are probably not immediately hostile. They're curious. They're investing enormous resources in exploration rather than weaponry. Fourth, they're either far away or long gone. If the civilization that built 3i Atlas were nearby and currently active, we'd probably see other signs: radio signals, engineering megastructures, activity. The silence suggests distance or time. Maybe they're hundreds of light years away, and this probe is an old mission, launched centuries ago, only now reaching our system. Maybe they were closer but have since moved, or evolved beyond recognizable technology, or gone extinct. Or maybe, this is a darker thought, they're deliberately staying hidden. They have technology to observe us without being detected, and 3i Atlas is the exception, the one probe that malfunctioned or was designed to be visible. We can't know without more data. But the speculation is fascinating. Fifth, if there's one probe, there are probably others. No civilization would send a single mission to a single star system and call it good. If you have the capability to build interstellar probes, you build many. You send them to multiple targets. You maximize your return on the enormous investment. So if 3i Atlas is artificial, there are likely similar objects visiting other star systems right now. Maybe thousands of them, scattered across the galaxy, each silently observing, collecting data, beaming information back to wherever. Maybe some of those probes have visited our system before. Maybe they visit periodically, every few thousand or million years, checking in on the local neighborhood. We wouldn't know unless we happened to have functioning astronomical surveys when they pass through. Imagine, right now, circling in the outer solar system beyond Neptune, there might be dormant probes from multiple civilizations parked in long-term orbits, occasionally waking up to observe when something interesting happens. We wouldn't see them. They'd be too small, too dark, too far away. But they'd be there, watching. It's a humbling thought. Or maybe I'm getting carried away. Maybe 3i Atlas is just an unusually symmetric comet, and all this speculation is premature. Maybe natural processes we don't yet understand can produce the observed features, and in 6 months we'll laugh about how excited we got over nothing. That's possible. Science has a long history of revolutionary discoveries that turned out to be mundane once properly understood. Pulsars were initially called LGM signals, little green men, because the regular pulses seemed artificial, turned out to be rapidly rotating neutron stars. Natural, if exotic. Fast radio bursts were mysterious and potentially artificial, turned out to be magnetar flares. Natural. The WOW signal picked up by SETI in 1977 looked like an artificial transmission. Still unexplained, but probably natural. The list goes on. Nature is weird. Nature produces phenomena that look designed but aren't. We're pattern recognition machines, and sometimes we see patterns that aren't meaningful. So yes, skepticism is warranted. Caution is appropriate. We shouldn't rush to conclusions, but we also shouldn't dismiss evidence just because it's uncomfortable. The history of science also includes examples of legitimate discoveries that were initially dismissed because they challenged prevailing assumptions. Continental drift was mocked for decades before being accepted. Heliocentrism was heresy, as meteorites were thought to be folklore. In each case, evidence eventually overwhelmed resistance, but progress was slower than it should have been because of intellectual conservatism. We need to balance openness with rigor. Consider all possibilities, but demand solid evidence. That's the scientific sweet spot. And right now, the evidence for 3i Atlas being artificial isn't conclusive, but it's substantial. It's enough to warrant serious investigation, enough to justify the observational campaigns being planned, enough to keep this story on the front page of astronomy journals. Over the next month, as new data arrives, we'll see which way the evidence tips. Will natural explanations emerge that elegantly account for all observations? Or will the artificial hypothesis strengthen as we rule out natural alternatives? I'm committed to following the data wherever it leads. If I'm wrong about this being potentially artificial, I'll publicly admit it and explain what we learned from the investigation. If the evidence increasingly supports artificiality, I'll say that too, regardless of how controversial it is. That's the scientist's responsibility. Honesty about uncertainty, transparency about reasoning, willingness to be wrong. What I can promise you is that we'll keep reporting the facts as we learn them. No hype, no sensationalism, no jumping to conclusions. Just careful, rigorous analysis of the best data we can collect. This is one of those rare moments in science when we're genuinely uncertain about something profound, when the answer could go either way, and either answer would be fascinating. When everyone from professional astronomers to amateur enthusiasts is watching the same datasets, running the same calculations, trying to solve the same mystery. It's science at its best. Collaborative, transparent, driven by curiosity rather than ego. And you're part of it. Everyone watching this, everyone discussing these observations, everyone thinking critically about the evidence, you're participating in the process. You're witnessing how science works when confronted with genuine mystery. That's valuable regardless of the outcome. So stay engaged, keep asking questions, demand evidence, think critically, and most importantly, stay curious. Because whether 3i Atlas is natural or artificial, whether it's a cosmic coincidence or a message from another civilization, the quest to understand it is making us better scientists, better thinkers, better explorers, and that's worth celebrating. The email arrived at 2:34 a.m. on February 3rd. Subject line, radar results, you need to see this. I was still awake, of course. Sleep had become optional over the past 2 weeks as data from multiple observation campaigns started trickling in. My coffee consumption had reached levels that probably violated several health guidelines. But when you're potentially documenting first contact with extraterrestrial technology, you don't worry about sleep schedules. I clicked the email open. It was from Sarah Chen, one of the lead researchers on the Goldstone radar team. We'd been corresponding for weeks, ever since the radar observations were scheduled. She'd been cautiously optimistic about getting usable data, but warned me repeatedly not to expect miracles. And 3i Atlas was small, distant, and radar returns would be weak. The email contained a single attachment, a PDF labeled atlas_radar_preliminary.pdf. My hand actually trembled as I clicked to download it. What I saw in that document changed everything. Let me back up and explain what happened over the past 2 weeks, because the radar data didn't arrive in isolation. It came as the culmination of multiple converging lines of evidence, each one adding weight to a conclusion that was becoming harder and harder to avoid. The high-resolution spectroscopy came first. 3 separate observatories, Keck, VLT, and Gemini North, all targeted 3i Atlas during optimal viewing windows. They used different instruments, different analysis pipelines, different research teams, independent verification built into the design. The spectra were exquisite. Resolution high enough to separate individual molecular emission lines. Signal-to-noise ratios 10 times better than earlier observations. This was the definitive chemical analysis we'd been waiting for, and the results were disturbing. All 3 observatories confirmed the anomalous composition. The expected organic molecules, formaldehyde, methanol, hydrogen cyanide, all the carbon-based compounds that should be abundant in a comet, were either completely absent or present at levels 100 times below normal. Instead, the dominant emission came from water and simple hydroxyl radicals. The spectrum looked clean, pure, almost sterile. Dr. Michael Torres at Keck put it bluntly in his preliminary report. This is not consistent with primordial solar system material. Either this object formed under highly unusual conditions that preferentially depleted carbon and nitrogen compounds, or the material has been processed. Processed. That word again. But it got stranger. When the teams looked at isotope ratios, comparing the relative abundances of different forms of the same element, they found something unexpected. Oxygen isotope ratios were slightly off, not dramatically. Not this definitely came from another star system level, but measurably different from the standard solar system values. The deviation was small, just a few percent, but well outside the error bars. 3 possible explanations. First, the object formed in an unusual region of the early solar system, where isotope ratios differed from the average. Possible, but requires special circumstances. Second, It's genuinely from another star system where formation conditions produce different ratios, also possible. Third, the material was isotopically separated through industrial processes. That third option, isotopic enrichment, is something we do here on Earth. Centrifuges spinning uranium hexafluoride gas to separate U-235 from U-238 for nuclear fuel. Mass spectrometers separating isotopes for research and medicine. It's a hallmark of advanced technology. Finding it in a comet would be unprecedented. The spectroscopy teams are being cautious. They're not claiming definitive isotopic enrichment. Not yet. The measurements are at the edge of what's possible with current instruments. They need confirmation from additional observations, but the preliminary data is suggestive, very suggestive. Then came the trajectory analysis. Multiple observatories had been tracking 3I Atlas's position for months, building up a comprehensive astrometric dataset. When the orbital mechanics team at JPL crunched the numbers, they found exactly what we'd been suspecting: significant non-gravitational accelerations. The object was deviating from a pure gravitational trajectory in measurable, consistent ways. The accelerations weren't huge. We're talking microgravity levels, tiny forces that would be imperceptible to a human but significant for orbital mechanics, and they weren't constant. They varied over time in a pattern that correlated with the observed jet activity. Here's what made it weird. The correlation was too good. For a natural comet, you expect rough correlation between outgassing and non-gravitational forces. More gas equals more thrust. But the relationship is messy because outgassing depends on surface properties, thermal conductivity, rotation state, all sorts of chaotic variables you can't predict precisely. For 3I Atlas, when you plotted the observed jet brightness against the measured acceleration, the points lined up. Not perfectly, there was scatter, but far more tightly than natural comets should show. It looked less like chaotic geology and more like controlled thrust. The JPL team identified something else. The accelerations appeared to come in discrete episodes. Periods of steady thrust followed by sudden shifts when the force direction changed. Then steady thrust again in the new direction. Natural outgassing evolves smoothly as the object rotates and solar heating changes. You don't get discrete episodes. But if you're firing thrusters in sequences, burn one engine, shut it off, fire a different engine, you'd get exactly this pattern. The lead analyst, Dr. James Kwok, included a note at the end of his report that I found particularly striking. The simplest model that fits the data is a system of 3 to 4 independently controlled thrust sources operating in coordinated sequences. Natural outgassing models require adding multiple free parameters to achieve equivalent fit quality. Translation: it's easier to explain the trajectory if you assume controlled thrusters than if you assume natural jets. Occam's razor, cutting the other way. The photometric monitoring campaign had been producing beautiful data. Dozens of observers worldwide contributing brightness measurements every clear night, building up a light curve with unprecedented time resolution and coverage. And that light curve was telling a story. The primary periodicity remained rock solid, 7.1 hours. Month after month, the rotation period didn't drift. For a natural comet experiencing asymmetric outgassing forces, you'd expect the period to change as torque spun the object up or down. We were seeing stability at the level of minutes per month, essentially unchanged. But there were subtleties in the light curve that became apparent only when you had comprehensive coverage. Small brightness fluctuations that weren't explained by the main rotation. Secondary periodicities hinting at precession or wobble modes. When analysts fit detailed shape models to the light curve, the best fit solution suggested an elongated object with an axis ratio around 1.6 to 1, shaped like a somewhat flattened cigar. And critically, the shape model was stable over time. The geometry wasn't evolving. For a natural comet losing mass through outgassing, shape evolution is expected. You're literally blowing material off the surface. The shape should change. But 3I Atlas maintained its form. Again, that word, maintained. Active preservation of configuration against forces that should alter it. The light curve also showed 3 minor features that might, emphasis on might, correspond to the 3 mini-jets. When analysts looked carefully at the brightness variations during each rotation, they found subtle enhancements at 120-degree intervals. like the jets were catching sunlight and creating small brightness spikes as they rotated into view. This was tentative. The signal was weak, near the noise threshold. But multiple analysts independently identified the same feature. It might be real. If it is, it's another confirmation of the geometric pattern, another data point stacking up. All of this, the spectroscopy, the trajectory analysis, the photometry, was converging on a consistent picture. Each piece of evidence, examined alone, was interesting but not definitive. But taken together, they formed a pattern, a coherent narrative. And that narrative was increasingly difficult to reconcile with natural origins. Which brings me back to that email at 2:34 a.m., the radar data. Radar observations had been attempted during 3 separate sessions in late January and early February. The geometry was favourable. 3i Atlas was relatively close to Earth, at a good angle for radar illumination. Goldstone transmitted powerful signals at the object, while both Goldstone and Greenbank listened for the faint echoes bouncing back. The first 2 sessions produced marginal results. The object was just barely detectable. You could see something in the data, but the signal-to-noise wasn't good enough for detailed analysis. Frustrating, but not unexpected given the object's size and distance. The third session, on February 2nd, was different. Atmospheric conditions were excellent. The object was at optimal position, and the integration time was longer. They accumulated signal for nearly 8 hours as the object rotated. When the radar engineers processed the data, combining all those hours of weak returns into a single enhanced image, they got something unexpected. They got structure. Sarah's PDF contained the radar image, technically called a delay Doppler map, but essentially a picture of the object reconstructed from radio echoes. The resolution wasn't great, you couldn't see fine details, but you could see overall shape and large-scale features. The object was definitely elongated, consistent with the light curve models. That was expected. But the radar showed something the light curves couldn't reveal. The elongation was smooth, regular, almost cylindrical. Natural comet nuclei are lumpy, irregular, covered in features from impacts and outgassing. When you image them with radar, you see complexity, rough surfaces, asymmetries, chaos. This was smooth. The surface texture suggested roughness at small scales. It wasn't mirror-polished, but the overall form was regular, geometrically defined. That alone was strange, but it got stranger. The radar team had analysed the polarization properties of the return signal. Different materials reflect radar waves with different polarization characteristics. Ice looks different from rock. Metal looks different from both. 3i Atlas showed mixed properties, predominantly consistent with ice, which made sense for a comet-like object. But there were hints, just hints, Sarah emphasized in her email, of higher density material in the interior. The radar couldn't penetrate deep enough to definitively map internal structure. But the return signal characteristics suggested the object wasn't homogeneous. There might be a denser core beneath the icy exterior. For a natural comet, you'd expect uniform composition, a mixture of ice and dust throughout. Some variation, sure, but not a clear core shell architecture. For a designed object, though, a core shell structure makes perfect sense. Put the sensitive payload equipment in a protected core, surround it with ice for radiation shielding, and as reaction mass for propulsion. The ice ablates away during perihelion, which looks like natural outgassing, but the core remains intact. It's exactly what we'd do if we were designing an interstellar probe. Sarah's email ended with a paragraph that I've read probably 50 times since. I need to be very clear. We're not claiming this is artificial. The data quality isn't high enough for definitive conclusions, but I've been analysing radar data from asteroids and comets for 15 years, and I've never seen anything quite like this. The regularity of the shape, the possible layered structure, the surface properties, it doesn't fit the profile of natural objects I'm familiar with. We need more observations, better data, but I thought you should know what we're seeing. I sat there staring at my monitor, watching the sky lighten outside my window. Dawn was coming. February 3rd was beginning, and I realised we're past the point of casual speculation. The evidence has weight now. Real, substantial weight. Not proof. Not yet, but enough that dismissing the artificial hypothesis requires ignoring significant data. That's a problem, because science doesn't ignore data. Over the next few days, I reached out to colleagues around the world, Informal conversations asking what they thought of the accumulating evidence. Not seeking validation, seeking honest critique, asking them to poke holes, find flaws, suggest alternative explanations. The responses were fascinating. People divided into 3 camps. Camp 1. It's definitely natural. We just don't understand the physics yet. These folks were committed to finding natural explanations regardless of how convoluted they had to be. And look, I respect that. Conservatism has value in science. Don't overturn paradigms lightly. But when I pressed them for specific mechanisms, how does nature produce 120-degree symmetry? How does it maintain that stability? How does it create isotopic anomalies? The answers got vague. Maybe there's some self-organizing process we haven't discovered. Maybe unusual formation conditions. Maybe we're misinterpreting the data. Maybe. At some point, maybe stops being a scientific argument and starts being wishful thinking. Camp 2. It might be artificial, but we can't be sure yet. The cautious middle ground. These were people genuinely on the fence, waiting for more evidence before committing. They acknowledged the anomalies, but weren't ready to make the leap. I have sympathy for this position. It's intellectually honest. The data is suggestive, but not conclusive. Reasonable people can disagree about interpretation, but some of these folks were also clearly uncomfortable with the implications. You could hear it in their voices. If it's artificial, that changes everything. That's too big. I need to be absolutely certain before I accept it. I understand the hesitation, but we can't let the magnitude of implications affect our assessment of evidence. Truth doesn't care whether we're comfortable with it. So in Camp 3, the evidence is compelling and we should seriously consider the artificial hypothesis. A smaller group, but growing. People who'd looked at all the data, done the probability calculations and concluded that natural explanations were becoming contrived. These weren't wild-eyed enthusiasts. They were careful, rigorous scientists who'd been skeptical initially, but were convinced by the mounting evidence. Their common refrain: I didn't want to believe this, but I can't ignore what the data is telling me. Dr. Rebecca Sandoval, a planetary scientist I've known for years, summarized it well. Look, I spent my career studying natural objects. I know how comets behave, and 3i Atlas isn't behaving like a comet. It's behaving like something maintaining itself against perturbations. That's what life does. That's what technology does. It's not what geology does. That distinction between passive and active systems kept coming up. Natural objects respond to their environment. They're shaped by forces acting on them. They erode, fragment, evolve chaotically. Active systems resist environmental forces. They maintain configuration. They show homeostasis. They persist. 3i Atlas is persisting in ways natural objects shouldn't. Now, I want to address the elephant in the room. What about professional astronomical organizations? What are NASA, ESA, major observatories saying officially? The answer is mostly silence, or carefully worded statements acknowledging unusual characteristics while avoiding definitive conclusions. This isn't a conspiracy, it's institutional caution. Large organizations move slowly, especially when dealing with controversial topics. They wait for peer review, for consensus, for unambiguous evidence. They can't afford to get excited about something that turns out to be mundane. But behind the scenes, there's intense interest. I know because I'm talking to people inside those organizations. They're analyzing the same data, running the same calculations, and many of them are quietly coming to the same conclusions we are. They just can't say so publicly. Not yet. Not until the evidence is ironclad and the conclusions peer-reviewed and published in major journals. That process takes time. Science isn't fast, but it's happening. Several papers are in preparation right now. Teams are compiling all the observations, spectroscopy, trajectory, radar, photometry, into comprehensive analyses. These papers will be submitted to journals like Nature or Science within weeks. Then begins the peer review process. Other scientists examining the work, checking calculations, suggesting improvements. If the papers survive peer review, and I think they will, they'll be published. And once published, the conclusions become part of the official scientific record. At that point, institutions can reference them, make official statements, take positions. We're maybe 2 to 3 months away from that happening. Spring 2026 could be when the scientific establishment formally acknowledges that 3i Atlas represents a genuine anomaly requiring serious consideration of artificial origins. Or the papers could be rejected, The data could be reinterpreted. Natural explanations could emerge that we haven't thought of yet. That's possible. Science is uncertain. We might be wrong. But I'm betting we're not wrong, because every new piece of data makes the artificial hypothesis stronger, not weaker. We're not cherry-picking evidence. We're following wherever the observations lead, and they keep leading the same direction. Let me share something that happened last week that crystallized my thinking. I was on a video call with a group of researchers, astronomers, planetary scientists, aerospace engineers, discussing the trajectory data. We were trying to model the non-gravitational forces, see if we could reconstruct what thrust profile would produce the observed orbital deviations. One of the engineers, Dr. Lisa Mahmood from JPL, pulled up a simulation. She'd programmed a simple model, an object with 3 small thrusters arranged at 120-degree intervals, plus 1 larger thruster along the main axis. She set the thrusters to fire in sequences, mimicking what might be an efficient attitude control and propulsion system. Then she ran the simulation forward, calculating how the orbit would evolve under those thrust patterns. The resulting trajectory matched 3i Atlas's observed orbit with stunning accuracy, better than any natural outgassing model, better than any other thruster configuration she'd tried. There was silence on the call after she showed the results. Then someone said, quietly, "That's not proof of anything. You can fit a trajectory with lots of different models if you have enough free parameters." True, but Lisa had used minimal parameters, just 3 small thrusters, 1 large thruster, a simple on-off firing pattern, no complex physics, no exotic mechanisms, just basic rocket propulsion, and it fit the data perfectly. Sometimes the simplest explanation really is the right one. After the call, I went for a walk. It was cold, clear night. I looked up at the stars and tried to wrap my head around what we might be documenting. If 3i Atlas is artificial, it means someone built it. Some civilization, somewhere, invested enormous resources in constructing an interstellar probe. They designed it, engineered it, launched it on a journey that would take decades or centuries to complete. And they did it with purpose. They wanted to explore, to learn, to reach out across the void and touch other star systems. We do the same thing. Voyager probes, Pioneer plaques, messages to potential extraterrestrial intelligence. Humans have always been explorers. We've always wanted to know what's beyond the horizon. It's humbling to think we might not be alone in that drive, that somewhere else some other species looked up at their sky and wondered, and then built machines to find answers. It's also terrifying in a way, because if we're seeing their probe, they might be seeing ours, or they might have seen us directly, studied us, documented our development. We might be on someone's list of interesting star systems with promising signs of emerging intelligence. What do they think of us? Are they watching, waiting, evaluating whether to make contact? Or is this probe ancient, launched by a civilization that's long gone, now just a ghost wandering the galaxy, still dutifully collecting data for creators who'll never receive it? We can't know, not from the data we have. But the questions themselves are profound. I'm getting philosophical, I know, but that's what happens when you spend weeks staring at data that might rewrite humanity's place in the universe. You can't help but think about the implications. Let me come back to practical matters. What happens next? More observations, obviously. The observational campaigns continue. Every telescope that can point at 3i Atlas is doing so, collecting data, building up the most comprehensive dataset ever assembled for a small solar system object. We need better radar data. The preliminary results are intriguing but not definitive. More observation sessions are scheduled for mid-February. If we can improve the signal quality, we might be able to definitively map internal structure. That would be game-changing. We need continued spectroscopy. Those isotope ratios need to be nailed down with higher precision. If they really are anomalous, if they show clear evidence of enrichment or unusual fractionation, that's a smoking gun. No natural process we know produces those signatures. We need to watch for any changes in behavior. If this is an artificial probe, it might do something unexpected as it swings through the inner solar system. Course corrections, trajectory adjustments, maybe even communications, burst transmissions back to wherever it came from. Our radio telescopes are listening. SETI facilities, normally pointed at distant stars, have turned toward 3i Atlas. They're monitoring across a broad range of frequencies, searching for any artificial signals. Nothing detected yet, but the search continues, and we need to prepare for what comes after confirmation. If the evidence becomes overwhelming, If the scientific community reaches consensus that this is genuinely artificial, what then? That's a conversation happening in small groups, in private meetings, in carefully worded emails. Because confirming extraterrestrial technology has implications far beyond astronomy. It impacts philosophy and religion, humanity's place in the cosmos, security, unknown capabilities and intentions, policy, international coordination on response science, new research priorities, funding allocation, public psychology, how people process such revelation. This isn't just a scientific discovery, it's a civilizational inflection point. Organizations are quietly preparing. NASA has protocols for contact scenarios developed back in the SETI heyday of the 1990s. They're dusting those off, updating them, or thinking through communication strategies. The International Astronomical Union has committees that would be activated if extraterrestrial intelligence were confirmed. They'd coordinate global scientific response, ensure data sharing, manage public communication. Governments have contingency plans. Most are classified, but they exist. Scenarios were gamed out decades ago during Cold War paranoia about alien contact being a Soviet hoax or vice versa. We're probably not going to need most of those plans. 3i Atlas isn't communicating. It's not demonstrating hostile intent. It's just passing through, observing, collecting data. If anything, the situation is anticlimactic. We might confirm artificial origin, and then nothing. The probe continues on its trajectory, eventually leaves the solar system. And we're left with knowledge but no interaction. That would be frustrating in a way. We'd know we're not alone, but we still wouldn't have contact. We'd be aware of the galaxy containing other civilizations, but still isolated from them. On the other hand, knowledge is valuable in itself. Knowing we're not alone changes everything, even if we can't talk to whoever made 3i Atlas. It means intelligence emerges. It means technological civilization is possible. It means we're not a unique cosmic accident. We're part of a broader pattern of complexity arising in the universe. That's profound. That's meaningful. That's worth knowing. I want to end this segment by acknowledging uncertainty, because despite everything I've shared, all the evidence, all the analysis, all the careful reasoning, I could be wrong. Maybe there's a natural explanation we haven't thought of. Maybe next week's data will point clearly toward ordinary comet origins. Maybe all these anomalies will collapse into mundane physics once we understand the situation better. I'm not attached to being right. I'm attached to understanding truth. If the truth is natural object with weird properties, I'll accept that. If the truth is artificial probe from another civilization, I'll accept that too. The process matters more than the conclusion. The fact that we're investigating rigorously, considering all possibilities, demanding evidence, that's what makes this science rather than speculation. So let's see where the evidence leads. Let's keep collecting data. Let's stay humble about what we know and honest about what we don't. And let's prepare for the possibility that February 2026 might be remembered as the month humanity found its first confirmed example of extraterrestrial technology. Or not. We'll see. Either way, it's one hell of a time to be alive.